In this screencast, I'm going to describe the operation of a triple effect evaporator where we have backward feed. There's a separate screencast that describes a triple effect evaporator with feed in the same direction that the steam is fed, and we'll see exactly what that means. For this backward feed system, we're going to feed into the third effect, so we'll call this the third, the second, and the first. I'm going to feed a dilute solution, for example a solid in water, and then our objective is to create a concentrated solution out of the first effect. And the idea of using a triple effect evaporator is that we use significantly less energy than a single effect. We can essentially, say for water, evaporate 3 kilograms of water for feeding in 1 kilogram of steam. So the way the evaporation is going to work in the various stages, what we're going to do is feed into the heat exchanger coil steam, and the outlet of this is going to be condensate, namely the steam that's condensed to liquid water. We use the energy from the steam to evaporate out of this first effect. What we're going to do with this vapor is use it now as the heating source for the second evaporator. So this means we're going to feed in now this steam again to the heat exchanger coil. Again, coming out, it's going to be liquid as we condense the steam. And that steam, of course, is going to evaporate. So we're going to have vapor. Let's call that vapor 2. Well, that vapor is then going to be fed into the heating coils for the third effect. And coming out of the third effect again is liquid water. So that's part of the steps of how we're getting the evaporation. And of course, in the third step means we're again forming vapor, which is the solvent. Well, we fed into this third effect a dilute solution. Because we're evaporating some of the liquid, of the solvent, we've made a more concentrated solution. So that means we have a more concentrated solution leaving the third effect. And we want to feed that now into the second effect. However, one consequence of running this system in the direction we're running it is that temperature 2 for this system, namely that's the temperature here, that's the temperature of the more concentrated material that's leaving here. So temperature 2 is going to be higher than temperature 3. So if we're going to feed the liquid coming out of the third effect into the second effect, and it becomes the feed for the second effect, we actually have to raise the pressure because pressure 3 is less than pressure 2, because we're talking about saturation temperature and a corresponding pressure. And we can't feed it in without raising the pressure. So that means we take out this more concentrated liquid. We have to use a pump to raise the pressure, and then we can feed the concentrated liquid into the second effect. And then the same thing, the outlet from the second effect, because again temperature 1 is greater than temperature 2, which means pressure 1 is greater than pressure 2. So the liquid leaving the second effect also needs a pump to raise its pressure so it can be fed into the first effect where it's concentrated to form our final concentrated solution. And so this describes the triple effect evaporator. A couple more things to point out. The mole fraction now in the liquid of our solute, X1 is greater than X2 is greater than X3. X3 is what's leaving here, X2 here, X1 here, and this would be X of the feed, and feed mole fraction is even lower. So this describes the operation where we take advantage of the vapor that we form in one effect as the heat source. And that's why T1 must be greater than T2 in order for it to be able to evaporate the liquid in the second effect. Likewise, the temperature 2 must be greater than temperature 3 to have a temperature difference so we can evaporate the formed vapor 3. There's a couple reasons why we might run the triple effect evaporator with this backward feed. One is if our fresh feed that's coming in here, that's our dilute solution, if our fresh feed is cold. The reason being now we'll take a smaller amount to heat it to our lowest temperature rather than heating it to our highest temperature. The second would be that as we concentrate the solute, the liquid becomes more viscous. So the viscosity increases as X increases, the mole fraction of the solute. And therefore we want the hottest temperature to be when we have the highest concentration of the solute, because the heat transfer is going to be higher when the material is less viscous, and at a higher temperature it's going to be less viscous. Other aspects of this are the same as the forward feed. An important aspect, of course, is that we can get a lot more evaporation for the same amount of feed of the steam. So this is the big cost in the process, separate from the capital cost, is the steam being provided to the system. And the more we can evaporate with that steam, the more economical the process is.